Hello and welcome. Today we'll be solving Cambridge O-Level Physics paper number 2. The code for this exam is 5054. This is May-June 2021 exam, and this is the version 2 of this paper. So let's start. The first is the section A. So we have to answer all questions in this section. So for the first part or the first question, it states that state the difference between a scalar quantity and a vector quantity. So we remember that for a scalar quantity is only defined by the magnitude, whereas a vector quantity is defined by the magnitude and direction. Right? So we always remember that the scalar quantity only have magnitude, whereas the vector quantity have both magnitude and direction. Sorry, has both magnitude and direction. So this part 2 of this question 1a, it says that state 2 examples of each quantity, scalar quantity. So remember, there are many examples. You can state any two. So for example, mass is a scalar quantity, distance is a scalar quantity, time is a scalar quantity, speed is a scalar quantity. Similarly, weight is a vector quantity, displacement is a vector quantity, force, for example, is a vector quantity, uh, and then acceleration is a vector quantity. And again, you only have to mention two, so make sure that you mention two quantities, and those quantities must be correct ones. So moving ahead, part B of this question, it says that figure 1.1 shows the direction and size of two vectors P and Q. So we have these two vectors. It says that in a space next to figure 1.1, draw a labeled vector diagram to show the resultant vector obtained by adding two vectors P and Q. Draw the vector P and Q and the resultant vector to the same scale. So the best way to draw is you will be drawing, measure the length. So for example, measure using a ruler, measure length of P and Q, and make sure that when you are drawing, they must be aligned or they must have similar shape. So I just request you to excuse my drawing over here. So make sure that whatever the length or you measure it from the rule, the P must be of similar length and must have similar direction or similar angles. Say for example, this is the angle theta, this is the angle theta. Make sure you have a or use up your protector or D over here, and from 0 degree align it to 0 degree, and then you can just align it your 0 degree here as well. And then at this point, draw your Q vector. Again, measure the distance for Q and make sure that Q vector is aligned in this fashion. Now you remember the parallelogram law, parallelogram rule for vector additions. So just make another vector Q equivalent vector and another equivalent vector P. So this is P, this is Q. So the resultant vector will be this one. This is your resultant vector R, and make sure you have resultant vector R equals to P plus Q, right? So this is where R dash is the resultant vector. The only things you have to make sure, the direction of these vectors must be aligned. the length of these both or your drawings must be the same, and your effective value or your the resultant vector would look something like this as per the parallelogram law of vector addition or rule of vector addition. Okay, so that this is our first question. So moving ahead, we have in question number 2, it says a car approaches traffic lights. The lights change to red at time t equals to 0. The figure 2.1 shows how the speed of the car changes with time. Okay, so this is the speed. This is the speed of the car and it changes with time. So it says that the car starts to slow down after certain starts to slow down a short time after the lights change to red. Determine the time between the lights changing to red and the car slowing down. So again, remember the car approaches the traffic lights, the lights change to red at time t equals to 0. So at time t equals to 0, the light approaches to red, changes time. So it says that the car slows down a short time after the giant changes to red. So slows down for a short distance of time. So it slows down till this point, and after that it decelerates. So it's a speed time graph. So we can measure the rate of change of speed. So till this point, we have to measure the time. So this is 1.1. This is there 2 spots. So and there are total of 1, 2, 3, 4, 5. So it is approximately 1.4 seconds. So t is determine the time between the lights changing to red and the car starts slowing down. So time is 1.4 seconds from the graph. So this is the point from the light changing red to the time it took from. So this the light changed red, the car continued with the same speed till this point, and at this point the car started to slow down or decelerate. So moving ahead, part B, it says that state what is meant by uniform acceleration. So uniform acceleration, there are many ways to define it. So you can always write that the speed, so it is acceleration. So we have to, the speed basically increases. And if there is uniform deceleration, the speed will be decreasing. The speed increases at a constant rate, throughout the journey. Okay, so this is one way of defining it. You can also say that the other way, or because we are given a graph, you can also say that, so you can write one. The other way of saying is the speed time graph remains constant. Sorry. The speed time graph remains constant or same. Any definition you can use for that. So whenever you are defining some, writing something like that, it's a good to draw a little graph over here for the examiner. So this is meters per second. This is your time. This is second. So a constant, it would be something like this. And this is your slope, delta V, delta T, something like that. Okay. And this is equal to, so yes, that's fine. And uniform acceleration. So acceleration is basically delta V by delta T. Okay, so again, it says that state how figure 2.1 shows deceleration of the car between 2 and 7 seconds, and then the deceleration is non-uniform. So basically, in our previous slide, we can say, so we have to tell, or let's label it, which would be helpful in giving our answers. So A, B, and C. So we have labeled 3 regions between say almost 2 seconds. So from this to this, so let's say at 2 seconds, I label it as A, right? So I leave it as it. So at 2 seconds, I label it at A, 4 seconds it is B, and 7 C. So just find out the slopes. So let's find slope AB and slope of BC. So if I find out the slope of AB, the slope of AB is basically rate of change of along the y-axis. So you can say delta y divided by delta x, and this is equal to minus 4.75 meters per second square. And similarly, if I find the slope for BC, again, change in y, for example, 8 over a, it is 8 over here, and it is 3, 8 by 3 is approximately minus 2.667 meters per second square. Okay, so these are the two slopes. And again, we can see from these slopes that the slopes are not constant or they're not same. And since there's a minus sign, the minus sign shows deceleration. And since both are not same, it means that that deceleration is not uniform. So here we can just simply write that from the graph, the deceleration from t equals to 2 to t equals to 4 seconds is 4.75 meters per second square, and from t equals to 4 to t equals to 7 seconds, it is 2.667 meters per second square. Since it is not constant, therefore it is non-uniform. As simple as that. So we can simply see it from a graph that this is not uniform. So again, it says that in the last part, determine the distance, or sorry, in part number C, it says that determine the distance the car travels from the moment the car slows down until it stops. So from again our previous slide, we can see that the car starts slowing down from around 1.4 second and it stops at time t equals to 7, right? So we have to basically find out distance between time 1.4 seconds to time 7 seconds. And for this case, we need to find out area under the graph for these two. So again, if we find out area under the graph, we can just simply see from our previous slide that we can divide it into two halves. So one is a area under the graph. This is so this part is so basically we have to find out the area of this part, and we also have to find out the area of this BC. Say let's label it. So if I call it as this point is X, this is not X. X is can cause confusion. So I call it as U V W, and we have it C and B. Okay, so area U V WB plus area B, C, and this W. Okay, so you just have to find out the areas. Area, first case, 1 by 2, sum of parallel sides. So we have to find out the sum of parallel sides. So 20 plus 8. Sum of parallel sides is 20 plus 8 multiplied by the height, and height is from 4 to 1.4, 4 minus 1.4, so it is 4 minus 1.4. This is the area, plus the other part is half the base is 3 into height is this is 3, the height is 8. So 8. So if we find out the area, it comes out to be 48.4 meters. So that will be our answer. So distance is 48.4 meters. Again, the units are very important. Do not forget to write the units. So this is how we solve this question. So moving ahead, next part, it says question number 3. Question number 3, it says that figure 3.1 shows a small brick hanging from a Newton meter. So it's a, remember, it's a Newton meter. It is measuring weight. Okay, so the reading is given on the Newton meter is 3 Newton meters. So the weight of the block is 3 Newton meters. Describe how the reading on Newton meter is used to find the mass of the block. So this is basically uh, uh, suspended in the air. So gravity is acting on it and it is giving you the weight. So weight equals to mg. So in order to find out the mass, m, that is m, we have to divide the reading of this divided by the gravity value. So if you take gravity as 10 meters per second square, that would be good. Or you can also take 9.8 meters per second square as well. So again, you have to just simply describe this process. So we know that the weight of the object is given as W equals to mg, where m is mass, W equals weight, and G is acceleration due to gravity. So assuming G equals to 10 meters per second square, comma, the mass can be calculated as 3 Newton divided by 10, 0.3 kg. Okay, or you can also say or 300 grams. Okay, so something like this, if you can just simply write it in words, that would be a good answer. Okay. Excuse me. So question number 3, part B, it says that the same brick, again, the same brick was of 3 Newton. So remember, this one was 3 Newton. And the Newton meter used as an apparatus in figure 3.2. The meter rule is pivoted at the center and is balanced. The reading on the Newton meter is not shown. Okay, so this is how it is balanced, and the reading on the Newton meter is not shown. State the principle of moments for a body in equilibrium. So remember, the principle states that the clockwise movements are equal to anti-clockwise movement around a pivot under equilibrium condition. So let's write it now. The principle of moments states that the clockwise moments are equal to anti-clockwise moments about the pivot under equilibrium. That you can also for a body. Okay, so this is how we can write the principle of moments for a body in an equilibrium. So the second part, it says that determine the reading on the Newton meter shown. Okay, so let's go over here. So this is 3. We know that this is a meter long, you can say foot or a meter long rule. So basically the pivot is this point. So one force that is acting, or the counterclockwise force is acting on this pivot is this, and the clockwise force acting on is this. This is the upward technically force that is going, and this is the downward force going, and this upward force will be reflected by on this Newton meter. So if we apply principle of moments across this pivot, we can say we call this force say F. So F is the upward force, and this is 3 Newton that is acting downwards. Okay. So what would be the case? So F multiply by, again, it is a good practice to use the units that are standard. It means that use meters. But again, you can use centimeter as well because the units cancel out on the other sides. But 20 divided by 100, we can go with the conventional method. And then we have the length of 20 plus 10, 30. And that 30 is acting downwards, multiply by, and the force is 3 Newtons. So this force is upward Newton, and this is the downward Newton. So this is the overall, again, this 30 is divided by 100. So going back, so what we saw that force F is acting upwards, multiply by 20 centimeters by 100. Similarly, 3 Newton force was acting, and 30 centimeters was the distance, and this distance is in meters. So just simply, we can just simply find out the value. The force will be 4.5 Newtons in this case, and this will be the reading on the Newton meter. And a good way is to show the reading something like this, 4.5 Newton. Okay, this is a good way of showing. Okay, so the part C of this question, it says that a beaker is placed so that the brick is partly submerged in the water. Okay, as shown in figure 3.3. The apparatus is adjusted to keep the rule horizontal. Okay, so just why the reading on the Newton meter is less. So remember, in water, if we put a weight, it causes weightlessness. It means that why or how, or for example, this is a 3 Newton 3 Newton, or the weight of this block is 3 Newton. But when you place it under water, the weight basically decreases. Not the mass changes, but actually the weight decreases. That happens because of the upward force, or the reaction force that acts on this block because of the water, or the Newton's third law. So that basically reaction force, so F dash, I call it FR. So that basically minuses, or the weight effective becomes actual weight minus the force that is acting, 3 Newtons that is acting on this in the reverse direction. So the effective weight basically decreases. So you can write weightlessness as well, but it's not a good answer. So it's so the good way to write is that so why the reading on the Newton meter is less? The reading is less because of the upward force acting on the 3 Newton block due to, sorry, due to water, This, so the reading is less because the upward force acting on the 3 Newton block due to water, something like this. And this basically again decreases the overall moment, and that basically effectively decreases the effective, or basically in that case, the effective, or you can say it is weightlessness reason, and this is the best way to write this answer. Okay, so next question, question number 4. It says, in a demonstration, a teacher uses a loud ticking clock, 2 hollow tubes A and B, and a barrier A and B, a barrier and a smooth surface. Okay, the clock is used as a source of sound. So the ticking of the clock, tick, 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 it's used as sound. This is hollow conduit. And again, the figure shows, figure 4.1 shows tube A and clock both fixed in a position on the left of the barrier. So sound from the ticking clock passes along tube A and is instant on the smooth surface. The student listens to the sound passing through tube B, which is on the right of the barrier. On the figure 4.1, draw the tube B in position where the sound heard by the student is the loudest. So remember, uh, sound travel in form of waves. So sound waves will be traveling something like this. Okay, so the direction of waves will be this. When they strike this part, they are incident on this smooth surface, then they will be reflected, right? So they will be reflected, and the reflected wave will be in this direction. And remember, law of reflection of waves, what it states: angle of incidence is equal to angle of reflections, especially if here we have a smooth surface. So if this is our angle of incidence, this will be our angle of reflection. So the maximum energy of the wave will be reflected across this. So if we have to hear the loudest sound, we have to make sure, or the student have to make sure the tube comes somewhere here. This is our tube B, and here is the ear. Okay, so this is how, or if you have to draw it on this on this paper, make sure you just law of reflection, theta incidence equals to theta reflection, so that your examiner knows that you know the law of reflection of waves, and you have used the concept you have learned in your course to the best of your knowledge, and always write answer number 1, the diagram. Okay, next part. So explain answer to number 1. So now we have to explain why we did it. So the sound, again, the sound waves, again, it's important, reflect from the smooth surface, the angle of reflection of reflection, okay, let's say theta r is equal to angle of incidence, all right, theta I, so the maximum energy of the wave will be concentrated across this direction of reflected wave. Okay, this is how it goes. So then the question part is the speed of sound in air is 330 meters per second. State typical value of speed of sounds in the air. Okay, so typical value generally it's good. It's about 5x. So multiply 5x times air. So this 5x times air is approximately equals to, you just multiply 1650 meters per second. So you can also always write 1650 meters per second. Always remember the speed of sound in solid ranges between 1000 meters per second to 10,000 meters per second in solids, right? So the speed of sound in solids is something between this, and so we are good about. So it is just generally um, the 5 times of whatever the value we have in here. Okay, so moving ahead, so we have question number 5. So question number 5, it says it shows a method of producing sandpaper using static electricity. Glue is sprayed on the moving paper. So the glue is sprayed on the moving paper. The sticky paper then passes between the two metal plates. So there is a glue. Remember, the glue is over here. The sticky paper then passes between the two metal plates. So the paper passes between these two metal plates. One of the plates is positive and the other is plate, and the other one of the plates is positive and the other plate is negative. There is an electric field between the plates. So there is an electric field. So this is positive, negative. So electric field is going from the positive to the negative plate. Okay. So on the first part, on figure 5.2, draw the electric field between the two plates. Show the direction of the electric field. Okay. So the electric field, again, this is the positive plate. This is the negative plate. So electric field will always be between from positive to negative. So you draw the electric field lines, make sure that these lines are equally spaced because that is a property of electric field. So make sure that these lines are equally spaced. And on the outside, draw a line like this. This is the fringing effect that happens at the boundaries. And that shows the examiner that you have a very good concept of this whole part. So again, the 2 points are for drawing equidistance line from positive to negative and showing this fringing effects. Okay, make sure that you do not make this mistake in the exam. Okay, next part says part B, the grains of sands are present just below the sticky paper. Each grain of sand is a conductor of electricity. Okay, so figure 5.3 shows 2 layers of grains of sand in the space between the two plates. Okay, so we have this negative plate, we have this positive plate, and then there is a space between there, and there is some grains over here. So question is, explain using ideas about movement of charge why the top layer of sand becomes positively charged. So top layer of sand becomes positively charged. So, okay, so this becomes positively charged. The question is why? And this is because of the electrostatic induction. Okay, the electrostatic induction. How? So have to explain it. So you just simply say that the static charges distribute over the sand particles. The negative charges. So for example, so these the bottom side would be negatively charged, and this part would be positive charge, because this negative charge will cause positive charges on this plate, and this positive charge will cause negative charges to come in this plate. And since this is in contact with this thing, these charges will be neutralized. So positive charges are not in contact. So they are technically will be pulled towards the negative plate, and in a way you can call it the sticky paper. Okay, the positive charges, the negative charges move. So the negative charges move to so these are the negative charges I'm talking about. So these negative charges we can call as move to the positive plate, or move towards, rather, not move towards the positive plate, uh, and the positive charges move towards the negative plate. So that is how it goes. So, and static charges, so these static charges are distributed in this fashion. So again, it says that state why the top layer of sand moves towards the sticky paper. The positive charge on the top layer is attracted to the negative plate. So basically these charge move in this direction, and when they move in this direction, they are actually caught by the sticky paper, positive shade, thereby getting stuck to the sticky paper. Okay, so these positive charges basically move towards this negative plate, and since the sticky paper is moving in this direction, they just are stuck to it and they are taken out. Okay, so next part, it says that a student receives an electric shock by walking across a certain type of carpet and then nearly touching a piece of earth metal with his hand. The potential difference between the hand and the metal is 2000 volts, and the charge transfer is 4 × 10 power minus 4 coulomb. Calculate the energy transferred when the spark jumps across the air gap from the metal onto his hand. So remember, we are given with voltage over here, and we are given with Q, or the value of charge. So remember, energy is given as Q times V, or charge times voltage. So just simply multiply 2000 by 4 into 10 to power minus 4 coulombs. This comes out to be around, in energy is in joules, so 0.8 joules. Okay, so simply 0.8, the unit J is fine. Okay, again 2 points calculation, and again remember, do not forget to mention the units. Okay, next part, question number 6. It says that the power input to a filament lamp when connected to a 12-volt supply is 20 watts. Okay, state what is meant by power. So power is amount of energy required to do useful work. Amount of energy required to do useful work per unit time. Okay, the amount of energy required to do useful work per unit time again is called power. It's up to you how you want to write it. So this is how the overall definition of power comes out to be. Then part B, question 6, part B, first part, the current in the filament. So I have to find out the current in the filament. So remember, the voltage is 12 volts, the power is 20 watts. So remember the formulas for power. Power is given as VI, power is given as I square R, power is given as V square by R. So these are the three power formulas for power. We are only given, or we have to find out the value of current. So the current we are given with voltage. Yes, we are given with the total power. So we are not given with the resistance. So we just have to find. So the first formula will give us our right value. So the I equals to P divided by V. So power is 20 divided by 12. So the answer is 1.6667 amperes. Again, do not forget the units. The units of current are ampere. Then the resistance of the filament. Again, we can use any of the formula. So we can use this formula for the resistance. So the resistance, again, power is 20, voltage is 12 square divided by R. R is the resistance. So my value of R comes out to be 7.2. Again, the units are ohms. Resistance is 7.2 ohms. Okay. Again, so this is how we do this. Then part C, the filament of another lamp is made from a thinner wire. Remember, it's a thinner wire of the same length and made from the same material. So material is the same, length is the same. Both lamps are connected to the same supply, okay? The 12-volt supply. State and explain how using the thinner filament affects the power input to the lamp. So remember, the resistance is given as rho times L divided by area. Okay, so technically, if we are using a thinner wire, so we are decreasing the area. However, the material is the same and the length is the same. So rho and length are constant. So basically, resistance is directly proportional to 1 by area. So if my area decreases, my overall resistance increases. Okay, so if my resistance increases, what happens to the power? So remember, we saw three different formulas for power. P equals to VI, P equals to I square R, and P equals to V square by R. So the best way in this example is to see that we are given with the voltage as well. So good to use this formula. So if the voltage remains same, power is inversely proportional to resistance. So if my resistance increases, my overall power decreases. So this is why we have to. So again, resistance increases, power decreases. So this is what we have to write it here in words. So just simply write the thinner wire filament will have more resistance. Okay. The resistance is inversely proportional to so the resistance is inversely proportional to the area. Sorry, as you can also, as the resistance is inversely proportional to the area. Okay. The power is given as V square by R for a constant voltage supply. The power decreases for a thinner filament lamp. Okay, so this is how you write this answer. And again, it's up to you how you use the words or the statements. But overall, the concept, remember, resistance is inversely proportional to area in our case, because the material and the length are constant. So material is defined by the resistivity, rho, and length are both are constant. So resistance is inversely proportional to area, and our power is also inversely proportional to resistance for constant voltage. So this is how it goes. Okay. So moving on, question number 7. Question number 7 shows, or the question number 7 says the figure 7.1 shows a simple DC electric motor. So this is a simple DC electric motor. The motor is connected to a battery with positive terminal of the battery connected to the terminal A. So remember, this is the positive terminal of the battery. This is the negative terminal of the battery. Okay. And the magnetic field lines are going in this fashion, north and south. Again, so if I draw the magnetic field lines, for example, this. Okay. First part, explain why the coil turns in the direction shown. So positive. So again, if the positive terminal is connected here and the negative terminal is connected, the motor is connected to a battery with positive. So the battery is connected here. So this is, so if a battery is connected, it means that it's a current carrying conductor. Okay, it's a current carrying conductor. So if it carries a current, so current flows from positive to negative. So this is the direction of current. So this is the direction of the current. So this is the direction of current. So again, explain why the coil turns. So we can simply write that according to Fleming's left hand rule, which states that current carrying conductor placed in a magnetic field such that the conductor the plane of the conductor is perpendicular it's good to write a current carrying loop slash coil slash conductor. Okay, plane is uh, perpendicular to the magnetic field so a current carrying conductor loop slash coil is placed in a magnetic field such that the plane of the conductor is perpendicular to the magnetic field, comma, it experiences a resultant force. Okay, and that resultant force, the direction of the resultant force, the direction of the force is determined by the, again, this Fleming's left hand rule. Okay, and this resultant force, this resultant force causes the coil to turn. Okay, and this basically, the resultant force causes the coil to turn about the axis. Something like this. Say this is the force down, this is the force up. Again, you can also write that in terms of that there is a resultant force that causes the coil to turn around the axis. You can just talk a little bit about the clockwise or anti-clockwise motion as well. But again, the direction is given, so that is fine. So this is how, or in a broader way, how you can explain what happens when a current carrying conductor is placed inside a magnetic field. Moving ahead, part B, the turning effect is increased when the coil wound on a soft iron cylinder. Explain why this happened. So when we place a soft iron cylinder over here between the magnetic field, so more magnetic field lines are uh, concentrated through that soft iron conductor, and in a way we have more flux linkage between the current carrying conductor and the uh, uh, and or you can just have say that more flux linkage between the conductor and the magnetic field lines, and eventually when it starts turning, or when the resultant force acts on it, the since there is more cutting of magnetic field lines, more will be the value, or higher will be the force, and that it starts turning, or it starts rotating with more speed. So explain why this happened. We can say that the soft iron cylinder increases the magnetic flux linkage, resulting in more cutting of magnetic field lines, thereby creating more force. More force means more rotational torque. Thereby more speed. Okay, again, these are the key concepts. Again, you can always use better choice of words, and in the better way to write this thing. Okay. Part B and question 2. Suggest one other way to increase the turning effect of the motor. Okay, so this is so one case is to have a soft iron cylinder. The other case is to increase the amount of current, or a bigger battery. You can use bigger magnets. You can use more number of turns on the coil. So you just have to write, say, more current from the battery. This is one way. Number 2, bigger magnets. Number 3, more turns of the coil. Okay, so these are some of the ways in which you can increase the overall rotational torque, or the overall speed of the rotation of the coil. Okay, so next question is question number 8. It says that figure 8.1 shows a potential divider circuit containing two resistors R1 and R2. So we have these two resistances R1 and R2. So the input voltage across these two resistances is 6 volts. and the R2 is the resistance across where we are taking the output voltage. So part A, it says that there is an input voltage of 6 volt. Okay, compare the tables and to show the output voltage of different values of resistance of the two resistance. Okay, so the resistance R1 8 ohms, R2 8. So if this is 8 ohms, this is 8 ohms. So basically find out the voltage. So for first part, basically we have to use the voltage divider rule here. We also call it as VDR. So using the voltage divider rule, so uh, simply voltage across R2 resistance is equal to R2 divided by R1 plus R2 multiplied by the input voltage V in. Okay, so the R2 is 8 volts, 8 ohms plus 8 plus 8 multiplied by 6. This comes out to be 3 volts. So my first value is 3. So again, this is one case. The second case is when the resistance R1 is 800, R2 is 1200. So again, use the same voltage divider rule. So 1200 divided by 1200 plus 800 multiplied by 6. So the output, the value is 3.6 volts. So in the second case, my value will be 3.6 case. Okay. So when you will be solving this question, do not forget to do this working. So without this working, there will be some loss of credit. Okay. So then there is a choice between it. So either you have to do this part and part this. So in this part, it says that the circuit shown in figure 8.1, the resistor R1 is replaced by a light dependent resistance. So again, the circuit shown was something. This was, say, for example, R1, this one was R2. This is my V output. This one was R1, was R2. This is, say, V in, okay? And this one was 6 volt. In the space, draw the symbol for the LDR. So the symbol for LDR is pretty simple, just shows the light shining on this. So this is a symbol for an LDR. Okay, so the LDR is moved from darkness into daylight. State what happens to the resistance of LDR and the output voltage. So the resistance of LDR decreases as it moves from dark to light. So the resistance decreases. So again, if the resistance decreases, so my R1 is, say, replaced by an LDR. LDR, and this is my output. This is 6 volt here. Okay. So if this resistance decreases, so what happens? So VDR, V output is R2 divided by R1 plus R2 into V in, right? So if my R1 decreases, so the value of R1 or my LDR technically is decreasing, what will happen to the output voltage or so the output voltage will increase. So my output voltage will increase, okay, or increases. Then it says the potential divider circuit can also be used to produce output voltage that changes with temperature, okay. State the name of the component that can be used instead of an LDR. So the simple thing is, it is a light dependent resistor. So we need a temperature dependent resistor. Remember, temperature dependent resistor. And what is its technical name? Its technical name is thermistor. Okay, so remember the temperature dependent resistor is actually a thermistor. So the name of the component. So the technical name of the component is thermistor. Some people may write temperature dependent resistor. It's a possibility that some of the examiners, or you may not be able to get complete credit for that. Okay. Then Or there is another choice. Again, it says a simple bistable circuit contains NOR gates. In the space below, draw the symbol for NOR gate. Remember, OR gate is drawn like this. This is my OR gate. Again, it's A, B, two input, one output OR gate. And if it's a NOR gate, you just simply do a bubble in front of it. So just simply make sure you draw it correctly. NOR gate. This is my, you can say, output. This is input 1. This is my input 2. Or another way, say A, this is B, this is output C. Again, so again, this is how you can draw the circuits. Again, good way to draw. Again, there is some, I just apologize for my drawing in this case. So again, part B, part 2, it says that describe what is meant by a bistable circuit. So bistable circuit, technically, or in electronics, it means that a circuit that has two stable states or two stable operating points. And generally, it's a digital circuit. So again, we have to write it down into words. The circuit having two stable operating states or switches between these two stable states. No, it's the circuit having two stable states. It switches between these two stable states when an input is applied. Okay, so this is how it goes. Say for example, example 0 and 1, or on state of state, and it basically is the way how our memory systems work, or it forms basis of the modern of basis for the memory circuits which we have in electronics. Okay, so these are some of the points which you can always write for when you have to describe a bistable circuit. Okay, so here what happens is that our section A part, or the compulsory questions which we have to solve in this part of the paper, that completes. And for section B, we basically have to answer 2 questions from this section. Definitely, I'll be solving all this all these questions available in this section for your simplicity. But let's start. So question number 9, it says that figure 9.1 represents the conversion of energy in a mobile phone. So we have a battery, some sort of, and that basically battery is inserted into that mobile phone, and then there is some energy output from. State the form of energy stored in the battery. So energy, this is looks like a lithium ion battery. So energy is stored in the form of chemical energy. Chemical energy. Again says part 2, state the useful form of output energy from the batteries. What is the useful form? So one of the useful forms is electrical energy. and basically this battery powers the circuit and electrical energy. Okay. State two useful forms of output energy from the mobile phone. So from this mobile phone, what are the useful forms of energy? So we can hear sound from sound energy. Okay. We can see light. Light is another form of energy. Okay. We can have some electromagnetic waves, electromagnetic waves, electromagnetic energy. We can also, for example, charge something else or use this as a source of electricity. So you can also say electrical energy. So these are some of the forms of energy which we can use or which we can see from or take from or in the energy output from the cell phone. Okay. Then question 9, part B. So it says when the battery is in use, the average current is 1.3 milliampere. Determine the charge that passes through the battery in time 2 minutes. So remember, charge Q equals to IT. The basic formula, the current is 1.3 milli. Time is 2 minutes. Convert it into seconds. The answer is 156 millicoulombs, or you can say it approximately 0.15, no, sorry, equals 1.56 coulombs. Okay, so just it's good to write 156 millicoulombs. So this is an answer, or 0.156 coulombs. Okay, moving ahead, part C, it says that a student estimates the thermal energy produced by the battery when the mobile phone is used and uses this value to estimate the energy and estimate the efficiency of the battery. He measures the temperature rise of 5 degrees centigrade when battery is in a period of time when the energy useful is 50 to 100 joules. The mass of battery is 110 grams. The specific heat capacity is this, 830 joules per kilogram degree centigrade. Calculate the thermal energy needed to raise the temperature of battery by 5 degrees centigrade. So remember the formula Q equals to mc delta T, or I write it as capital or delta, basically mc delta theta, where m is mass, m is mass is 110 grams, specific heat capacity 830 joules per kg centigrade, and delta theta is change in temperature. Okay, we have the change in temperature is 5 degrees centigrade, mass is 110 divided by 1000, that is in kg. Remember, mass is in kg. Multiply by 830 joules per kg per degree centigrade, multiply by 5 degrees C. Okay, so remember the units are very important. So the Q is 456.5 joules. Okay, so this is how you calculate the energy. So thermal energy required is 456.5 joules. Okay, so this is how you calculate this. Then it says state what is meant by efficiency. Okay, so efficiency is the basically defined as uh, defined as ratio of useful power, or you can say energy, to the total power or energy. Okay, so efficiency is the ratio. One definite. So calculate the efficiency of the battery. Okay, so now we have to basically calculate the efficiency of the battery. So the system we are having over here is, say, for example, this is say input, power input. We are having some power output and some energy that is lost is here. That is which we calculated E thermal. So so energy in, energy out. So energy out is 5200. Energy thermal is 456.5 joules. So efficiency again, E output over E input. So E output is, say, for example, 5200 divided by 4565.5 plus 5200. That is, or if input is basically whatever the energy lost and whatever we got at the output, assuming that we have no other sources of loss. So the efficiency turns out to be approximately 91.929%. So a quick approximately 91.93%. So you can write it as 91.93, or you can say 92%. But it's always good to go to up to 3 significant figures, or 9. This way of writing, or this is the best way. So again, part 4, it says suggest and explain one reason why the value of efficiency in 3 is larger than the actual efficiency of the battery. So remember that actual efficiency is around 70-80%. So on why this value is larger, and this value can be larger because of many reasons. So first reason is that we are basically assuming that this is the, or we are told that this is the output energy that is available, and this is the thermal energy that is lost. Okay, so there are many ways in which this thing can be faulty. For example, the thermal energy lost to environment is not included. So this is the just thermal energy that is required or need to raise the temperature. That is basically used by the battery itself to raise its temperature. But it's so no information about how much energy is lost to the um, environment is given. Okay, then there is no information about how much energy is lost in the electrical contents of the battery. For example, there are some interconnects inside the battery that connects various electrical components. There is some sort of energy or power that is lost in that. There is no way that information was given. And then there may be error in measuring these measurements. So we are measuring these so this is can be. So one way we can say energy lost to, or you can say not energy, so heat energy basically, or thermal energy lost to the surroundings. Thermal energy lost to surroundings is not included. Another way is energy lost in electrical interconnects is not included. We have error in measurements, can have slash faulty measurements. There can be any reasons. So suggest and explain one reason why the value of energy efficiency in 3 is larger than the actual energy efficiency of the battery. So if actual energy efficiency, for example, you have to calculate, you have to basically E out divided by E thermal plus E out. This one was which we used plus E ambient plus say E electrical. Okay, so if we add these values and multiply it by 100, so energy and actual will be much less than and calculated earlier. Okay, so and calculated this one is much less than, also an actual is much less than the energy which we calculated earlier. Okay, so this is how we can write or we can solve that question. So moving ahead, question number 10. Question number 10, it says that figure 10.1 shows a water wave moving from shallow water to deep water. The wavefront shown represent the crests of the wave. Now, these are the crests of the wave. So this is shallow water, this is deep water. So again, this is our wavefront. So one wavefront, two, three. Again, these are the wavefronts. So again, the wave is made up of dipping a wooden bar up and down in the water. The bar makes 10 complete up and down in 5 seconds. Okay. So determine the wavelength of the wave in the shallow water. So wavelength of the wave in the shallow water. So the easiest way of finding the wavelength. So lambda is, so we have 1, 2, 3, 4 waves. So 12 divided by 4. So the lambda is 3 centimeter. So the best way is to 3 centimeter using this information. Okay. So because this is the distance, or the lambda wavelength is the distance between the two crests or two troughs. So the only crests are shown. So the distance between two crests. So crest 1, 2, 3, 4, 5. So distance between two crests is our wavelength. So it's the easiest way. Then calculate the frequency of the wave produced. So frequency, it gives us information. 10 complete up and downs in 5 seconds. So 10 divided by 5, we have 2 per second. Okay, so 2 per second. So this is frequency, and this means 2 hertz. So the frequency is 2 hertz. Again, the speed of water wave in the shallow water. So we are given the frequency and wavelength. So we know that V equals to F lambda for a wave. F is frequency, 2 hertz. Wavelength is 3 centimeter divided by 100. So we have 0.06 meters per second. So again, why I did that, I can also always write centimeters per second, but it's a good practice to use the standard SI units, 6 meters per second. Okay, or you can say 6 centimeters per second. That is also a correct answer, but again, it's good to use the good scientific practice. Okay, so question number question number 10 is part 4. It says on figure 10.2, draw lines to show what happens to the wavelength and the frequency of wavelength, the frequency and the speed of water as it enters to deep water. So remember what is happening. So this is say the wave in the shallow water, then it goes to the deep water. Okay. So the key thing we have to understand is that that is a ripple tank we are having, and we are having a up and down. This thing is going up and down. So the frequency is fixed. So we have the fixed frequency. This is the key concept here, because sometimes people make mistakes. V equals to F lambda. So wavelength here is more, less, wavelength here is more. So wavelength is more, wave there. So they just simply do this mistake. So frequency stays the same. So it stays the same. And wavelength is increasing. So what happens to the speed? So now if the frequency is fixed, wavelength is increasing, what happens to the speed? The speed also increases. The speed also increases. So generally the mistake they simply do is that, okay, the wavelength is increasing, the wavelength is increasing, the frequency will decrease. So the frequency will decrease. No, that the frequency is fixed over here. So that is the key important concept. Do not uh, equals to f lambda. Okay, so this constant will remain fixed. Okay. Mm. So this is how we just simply go it. Not okay. So this is the base v equals to f lambda. Frequency increases, wavelength also increases. Okay. Next part. So in this, it says that the direction and the boundary is now altered. The water now enters the deep water from shallow water at an angle. So remember, this is shallow water. And this is deep water. So remember, shallow water is a denser medium. Deep water is a rarer medium. Rare medium. Okay, so denser, rare medium. So, and your light, or sorry, and your wave is going in this direction. So say for example, wave, this is the direction of your wave. So this is the direction of the wave. So the best way is to draw a perpendicular here. So draw a perpendicular here. Okay. So this is now the angle of incidence of this wave, and this wave will be okay. So this is the angle of incidence of the wave. So remember, when you enter from denser to rarer, you move. This is a key thing, denser to rarer, away from the normal. So you have to move away from the normal. Okay, so this is your normal. This is the normal direction. And I have, or the wave must have to move away from the normal. Okay, so away from the normal. Say, for example, this is the way it goes. So this is the way it goes. So now how this crest will look like. So it will just be something like this. So I draw here, I draw here, I draw here. Okay. So these will be the three lines we can use, and we can always go and continue them in this fashion. So for example, denser to rarer, away from the normal. So the thing we have to understand is that the lambda 1, and this will be our, say, lambda 2. So lambda 2 will be greater than lambda 1. This is another thing we have to make sure. So when we will be drawing, so draw the wave fronts on this deep water. So when we have to draw it, we have to draw it in this fashion. And so this is the direction of wave, or this the arrow that is shown. So, or you can always show an arrow, something like this. Okay, you can always show a direction of wave that goes in this direction, and the wave fronts, if you have to draw the wave fronts like this. So apology, sorry, my bad. Whenever you're drawing this, make sure these are parallel to each other. This is having an angle 90 degree with this direction of wave, just like this. This direction is at 90 degree with this. This must be at 90 degree. And this is the normal. It's not the wavefront. This is the normal. So wave angle of incidence. This is the angle of incidence. Technically, it will reflect at an angle of reflection, and it will refract. So this is basically our refracted wave. So this is our refracted wave, and this refracted wave moves away from the normal. So just, it's up to you how much you want to go away from the normal, because no refractive indices are given over here. and we are not much concerned. So we just have to uh, keep in mind a few concepts. Few concepts is that when we move from shallow to deep water, we move away from the normal, or the wave, whatever at the angle it is incidence, it moves away from the normal. And the lambda 2 is greater than lambda 1, or the wavefronts or the wavelength increases as it goes from shallow to deep water, or denser to rarer medium. Okay, so moving ahead, next part, it says white light is made up of different colors. Okay, so white light is made up of different colors. State the name of 4 colors in the visible spectrum and place them in order from the smallest wavelength to the largest wavelength. So remember, uh, visible spectrum is something between 400 nanometers to 700 nanometers. Okay, so 400 nanometers to, so and then we have ultraviolet, and we have infrared. Okay, so we have these two things. So ultraviolet generally is the lower wavelengths, so UV, so ultraviolet, and we have VIBGYOR, VIBGYOR. So violet, indigo, blue, green, yellow, orange, red. Okay, smallest wavelength, you can now select any. So this is my wavelength. This is lambda wavelength. So smallest, so you can use any combination: violet, indigo, indigo, blue, yellow, orange. So blue, I forgot green, yellow, orange, and red. Okay, so this is my WebGear or my overall spectrum. Just select 4, but make sure you go with this same scheme. Okay, then a narrow beam of part 2, it says a narrow beam of light can be split into different colors. Figure 10.4 shows the ray of light, shows rays of white light emitted from lamp. Okay, complete figure 10.4 to show a narrow beam is produced from these rays. How a spectrum look like on a screen, label your diagram. Okay, so we have to see the light spectrum. So you need to have a pinhole, a cardboard pinhole. Then you need to have a big prism or glass prism. Okay, so this is, say, for example, pinhole. This is your cardboard wood sheet. This is glass prism. Okay, so you can always say light coming here, and glass again it refracts, and again and there will be this light is reflecting 1, 2, 3, 4, 5, 6, 7. Okay, so this one will be violet. This is indigo. This is blue. Green. Then we have yellow, have orange, and we have red. Okay, and this is the light. beam. So again, how a narrow beam of light is produced. Narrow beam of light is produced with the help of a pinhole, and how the spectrum is looked like on the screen. So this is how the spectrum on your screen. This is how it will look like. So it's always good to show these two lights beams. So it basically shows the examiner that the student have concept about the refraction of light or the bending of light when it passes through a glass prism or a medium of having a higher refractive index. And again, uh, we have to basically show it like this. Which bends most, which color appears where, violet appears up and red appears down. And so in this fashion, okay. Uh, then uh, uh, moving ahead, uh, question number 11. It says a highly radioactive source uh, emits beta particles is placed a few centimeters away from a detector as shown. State the name of particle that has the same mass and charge as beta particle. So beta particle, remember, beta particle is 0 minus 1. So again, this is equal to electron. State and explain why metal casing is used. Okay. So again, we have 2 points. So why metal casing? Number 1, safety / handling. Okay. Number 2, it blocks, excuse me, beta particles emitting from the source to the surroundings. Okay. So safety, handling again, and the second cat is the metal casing blocks the radiation to, or the beta particles emitting to the surroundings from the source. Okay. Then it says state and explain what happens to the number of particles detected in a minute as the radioactive source is moved a few centimeters further away from the source. So now what you have done, so you have done is that you have moved this detector away from the source. So it says a few centimeter away from the source. So now you're away from the source. Remember, beta particles are electrons. They do not have intensity to travel long distances. So if you move away from the source, the intensity decreases. A few centimeters away from the source. Uh, so state and explain what happens to the number of particles. The number of particles shall decrease as penetration distance of beta particles is not very large. Decrease. Okay. So the penetration distance is not very large, so will decrease, or you can say uh, a slight decrease on the reading shall be observed. Okay, more than a meter away from the source. Okay, so this case, very significant change on the reading very few beta particles will reach the detector. And uh, penetration, because it's a meter away from the source, penetration of beta particles is not large, because penetration strength or penetration of very large. Okay, so this is how, these are some of the points which we can say that. Then part D, it says a nucleus of strontium 90 Sr90 decays by beta emission to the nucleus of yttrium. Complete the decay equation of this decay. So remember, beta is 0 minus 1. So 0, it remains 90, and there is minus 1, so it is 39. Just add, make sure you get the right answers. So make sure you get, after addition, you basically get 90 here and 30 here. Okay, last part. So part E, it says nuclear fission and fusion reaction both release large amount of energy. Describe how the process of nuclear fission differs from the nuclear fusion is differs from the nuclear fission. So again, this is 3 points question. So we'll try to make sure that we have three, at least 3 good points. So first case, so in fission reaction, the nucleus splits into 2 smaller or lighter elements, whereas in fusion reaction, 2 small nuclei are combined to form a heavy element. Okay, one case. Then in fission reaction, accelerated neutrons are required, are bombarded on a critical mass on critical mass of the radioactive element to start the reaction, whereas no such thing is required, whereas no such thing is needed for fusion. Although we have to keep in mind that in order we need very large temperatures for fusion reaction, and in order to achieve that we may need to have a first a fission reaction, and then in order to merge those two elements or two nuclei together. So, and third pair, energy released in fusion is much larger than the fission reaction. Or in some cases, you can solve this as fusion reaction, planets, stars, sun. Fission reaction is atom bombs, nuclear power plants, things like this. Okay. So these are some of the points which can be used or can to answer this question. Then part two, it says describe the conditions needed for fission reaction to take place. First condition, very high temperatures. Very high temperatures. Number two, very high pressures. Very high pressure. Number three, abundant supply. Supply of source nuclei. Okay. And very high speed of particles under these high temperature and uh, pressure. Okay, so these are some of the so nuclei, you can also say that abundant supply of atoms which we need to merge, very high temperature, extremely high pressure, and then abundant supply of or the sorry very high speed of particles that are we need to combine. So here this is the last part of our paper, and I hope you have enjoyed this discussion or reading. If you have any questions, please do use the chat box. I apologize for my pretty bad handwriting in this video. And if you have any questions or please feel free to ask in the chat, and best of luck for your exams and for your future. Thank you.